How do we find the distance between two lines? Well, if you're working in two dimensions like this, for one, the lines must be parallel, because if you're working in two dimensions and the lines aren't parallel, it means that the lines intersect at some point and suddenly the question is no longer applicable or relevant. So if the lines are parallel, you can simply pick a random point on one of those lines, and you can find the distance between that point and the other line, okay, where this is a 90-degree angle. Now, I've already explained this process in a previous video, so I'll link that here. Go check it out if you want to know how to do this. The rest of the video is going to focus on 3D scenarios. So what to do if your lines exist in 3 dimensions. Now, 3-dimensional lines can have a few different types of relationships. They can intersect each other, which again would be irrelevant, right? This type of question would not be applicable if two lines intersect one another. They could also be parallel, but if they are parallel, you simply pick a point on one of those lines and you follow the strategy I've outlined in this video here for calculating the distance between a point and a line in 3D. The other relationship is the lines could be skew, and skew lines is what we're going to focus on in this video because the process for that is very different. So let's say you have two lines just like this. You have this red line and you have this blue line. I have the equations for each of these lines. The first line I'll call line 1. This is my red line. It has the equation 4, 0, 0 plus t times -1, -1, 0. Again, this is my red line here. Then I have my line 2, which is my blue line. And this line has the equation 0, 0, 4 plus a times 2, -2, 1. And the first thing I'm going to do is I'm going to pick a random point on each line. So for my line 1, the red line here, I'm going to pick this point, okay? And for my blue line, I'm going to pick this point over here. Now, to pick two random points on the lines, you could just simply use these position vectors, but I'm not going to do that, and I'm just going to do it differently simply because my drawing, I want to have my points a little bit farther apart just to make this diagram look a little bit more clear, but you could simply use those two position vectors as your points if you wish. Instead, the points that I'm going to use, I'll say P1 for the point on line 1. This is the point 7, 3, 0, and the way I found that point was I just plugged in a random value for t. I believed I plugged in the value -3, and then I found this point. 4 plus -3 times -1, that gives you 7. I did the same thing for those other values, and that's how I got all of these. Now that's P1. I also have P2, this blue point here, and that has the coordinates -2, 2, 3. Okay, and the way I found that, I simply plugged in a value of -1 for A, and then calculated that point. So that's all I did. Again, you could simply use these position vectors as your points instead, but I decided to use these other points just to make my diagram look a little bit more appealing to me. Now that you've done this, the next thing you're going to want to do is create a vector that goes from the point P1 to P2, just like this orange vector here. And this is important because eventually we're going to want to find a vector that goes between the two lines like this, but is perpendicular to both. It will be the shortest distance between each line. This orange vector doesn't do that. There are several shorter vectors than that orange vector that can go between these lines. But for now, let's just start with that. Now, how could we find a vector that is perpendicular to each of these lines? Well, take a look at this, what I'm about to do here. Notice this red vector here that lies along the red line. That is a vector that you could simply get from your direction vector of L1, okay? And in fact, that's what I did. I took the direction vector of L1, the first line, the red line, and that is that little vector there. Now take a look at this vector up here, this blue vector that's running along the blue line. That blue vector I just got from the direction vector of line 2, okay? Hopefully that makes sense how you can do that, right? The direction vector just represents a vector that lies along your line. So I took those two vectors and I'm showing those here in the diagram. Now, what am I doing with these two vectors? Well, remember what I said, I want a vector that's perpendicular to both lines. And because those vectors are on the lines, I really need a vector that's perpendicular to both of those vectors. How do you come up with that? Well, you do a cross product, right? If you take the cross product of those two vectors, you can find a vector that's perpendicular to both. Now, how do I find the cross product of those two vectors if they're not even touching one another? Well, remember, vectors can move, right? I can move this blue vector down here like this, and now you see that these two vectors are touching tail to tail, right? And I can take the cross product, and when you do the cross product, you get a vector perpendicular to each. It looks like this green vector here. Now, we can actually do the math, right? Let me scroll down here. Let's do the cross product of those two direction vectors. Remember, the direction vectors were -1, -1, 0, and 2, -2, 1. Okay, those are my two direction vectors from those two line equations. I take those, I do the cross product, and what am I going to get? Well, you set up your matrix like this, your I, J, K, -1, -1, 0, 2, -2, 1. Now what will this equal? It equals your small matrix times I minus small matrix times J plus small matrix times K. What numbers go here? You cross out I, you're left with -1, 0, -2, 1. -1, 0, -2, 1. Over here, same thing. You cross out J, you're left with -1, 0, 2, 1. -1, 0, 2, 1. K, you cross out K, you're left with -1, -1, 2, -2. -1, -1, 2, -2. Now we do these calculations. -1 times 1 is -1, minus 0 times -2 is 0, so you're just left with -1 times I. Over here, -1 times 1 is -1, minus 0 times 2 is 0, so you're left with -1, but it's minus -1, so that's plus 1j, and you don't really have to write the 1, you could just say plus j, but I'm going to leave it as plus 1. And then over here, you're going to have -1 times -2, which is 2, minus -1 times 2, which is -2. So what's 2 minus -2? Well, that's going to give you 4k. And that means that we have the vector -1, 1, 4. And -1, 1, 4 is in fact the vector here that you see in my diagram, this green vector here. Now, what do we notice about the green vector? Well, it's perpendicular to both the red line and the blue line, right? If that green line was touching the blue line, you'd see they meet at 90 degrees. But that's the problem, right? It doesn't quite meet the blue line. So we have one vector here that's perpendicular to both, but it doesn't reach both lines. And we have the orange vector here, which goes from one line to the other, but it's not perpendicular to both. So we need a vector that has both of those properties, right? That is perpendicular to both lines and goes from one line to the other. So how can we achieve this? How can we find a vector that does that? Well, what you're going to want to do is take the projection of the orange vector onto the green vector, this normal vector. We call it the normal vector because it's perpendicular to both the red and blue lines. So we're going to project the orange vector onto the green vector. And when you do that projection, you're going to get a vector that goes in the direction of this green vector, but has a magnitude sufficient to get it from the red line to the blue line. So we talked about projection in a video previously. You can check that video out here if you'd like. But we're just going to do our projection here. Now, keep in mind when we do our projection, the projection of, and I'm going to call that orange vector, vector v. So the projection of vector v onto vector n, I'm calling that green vector, vector n, because it's the normal vector, right? It's perpendicular. This will equal vector v dotted with vector n divided by the magnitude of vector n squared multiplied by vector n. Now, doing this calculation will give you a vector where the green normal vector is that reaches the blue line, right? But we're not asked to find that vector, right? We don't really care about finding that vector. What we care about is finding the distance or the magnitude of this vector instead. And so if you only want the distance, instead what you can do is you can simply say vector v dotted with vector n divided by the magnitude of vector n. And the reason this works is because the projection is actually equal to this thing multiplied by n over the magnitude of n. If you go back and watch my projection video, you'll see that we develop the equation, right? This projection equation, and this is the step that comes before this. We simplify this to turn it into this. So if all you want is the distance, all you have to do is use this. If you want the actual projection, if you want the actual vector, then you can use this first equation. In this case, we only want the distance, so we can simply find this. Now, what is the dot product between v and n? Well, what is v, right? What is the vector v? The vector v was that orange vector here, but did we ever say what that was? It goes from point P1 to point P2, right? So I think we should say vector v is equal to P2 minus P1. And if you recall what those points are, P2 is -2, 2, and 3, right? -2, 2, 3. And P1 was 7, 3, 0. So we should subtract these values first and use that as our vector v. So vector v will be -2 minus 7 is -9. 2 minus 3 is -1, and 3 minus 0 is 3. So this is our vector v. So we take that vector and we do the dot product with vector n, the normal vector, that green vector here. What is the green vector? Well, we said up here it was -1, 1, and 4. Okay, so we're going to do the dot product between -9, -1, 3, and -1, 1, 4. And after we do that dot product, we're going to divide by the magnitude of vector n, which is just -1 squared plus 1 squared plus 4 squared, all square rooted. Okay, so let's do this calculation. Dot product, -9 times -1 plus -1 times 1 plus 3 times 4 divided by the square root of 1 plus 1 plus 16. Square all those values. And I'm just going to plug this into my calculator right now and see what I get. So we end up getting 20 over the square root of 18. And if we would like an approximation for this, we get about 4.714. So 4.714. So that's the distance between the two lines, the shortest distance between this red line and this blue line. So if this green vector we made a little bit longer so that it was able to touch the blue line, that would be the distance, 4.714 approximately. Hopefully this makes sense.